Believe it or not, we are now entering our final unit of the year. Woohoo! What we will do is we'll take the last 2 chapters and make 3 total sets of notes, put those together for 1 chapter test, and then of course get ready for the final exam. We'll look at chapter 21 all together this time, and we'll break down chapter 22 into 2 sessions, and again, put all 3 sets together as one. Are we ready? Here we go. The electromagnetic spectrum shows up as what we call electromagnetic waves, and where you see EM up at the top, that really is the abbreviation for electromagnetic waves. So as long as you know what EM means, you're fine writing just EM. Remember, God created the sun on day 4, as you saw on the title page. All energy comes from the sun to the earth in the form of what we call sunlight. All electromagnetic waves are transverse waves. Remember, that's the kind that goes up, down, up, down, up, down. Sound waves are the longitudinal ones that squeeze together. But all electromagnetic waves are transverse, which is not exactly 100% this, but kind of a fancy term for light waves. EM waves do not need a medium, whereas sound must have something to travel through because the molecules of the medium is what transfers the sound energy. Electromagnetic waves do not need a medium. These things can travel through absolutely nothing, such as through outer space. And that's great because if that wasn't the case, we would get no sunlight, which means we'd have no heat and no light. We would not survive. God knows what he's doing. Most EM waves are invisible. In fact, there are actually more invisible forms of light than there are visible. There are only 7 visible forms of light, and all the different colors that we see come from combinations of those 7. Now, there's a theory that says electromagnetic waves may actually have the teeniest, tiniest bits of solid matter. And that theory came because it was discovered that gravity can have a very, very, very slight pull down on EM waves. And in order for something to be affected by gravity, that something must have mass. So the very teeniest, tiniest amounts of mass that can happen are thought to be in electromagnetic waves. But remember, all energy comes from the sun in the form of electromagnetic radiation. Ready? Here you see a picture of what electromagnetic wave really is. Notice there are 2 waves here. They're both transverse. One has a magnetic field. The blue is what I'm pointing to there. The other has an electric field, pointing to the red in this image here. Electric field, magnetic field, electromagnetic wave. Amazing how things in science get their names. Both the electrical and the magnetic fields make up the EM wave. And we have both kinds of fields as we just talked about. I want you to notice, look at the picture. These are actually perpendicular to each other. And it's kind of like a book here. Let me grab a book and show you. Assume that I have that at just a right angle, 90-degree angle right there. Now what happens is the wave doesn't just travel as a straight line. Hopefully this will show up on your screen, but can you see that the stick is turning as the wave moves? So this is going to spin while traveling in an almost, but not exactly, a straight line. Because remember, gravity has a very, very slightest pull on an EM wave once that wave gets inside the Earth's atmosphere. Now, we said this before with sound waves. The higher the frequency, the more energy the wave has, which in visible light would mean a brighter light to our eyes. And also remember that frequency and wavelength go opposite of each other. If the frequency gets higher, then the wavelength gets shorter. And that's how we can put more waves in the same amount of space, a shorter wavelength from a higher frequency. And the converse is true also. A lower frequency would mean less energy and a longer wavelength, as we will discuss in our assignments. Ready? Speed of light we've talked about a few times before. Now let's compare. Baseball, my favorite sport, the best sport ever invented. Center fielders out there, or you're in the bleachers behind center field, what happens is we see the ball leave the bat from the batter, and then a moment later we hear the pop of the ball and bat connecting with each other. And that's because light travels a whole lot faster than sound. At normal temperatures and conditions, sound waves, remember, travel at approximately 345 meters per second. But look at the speed of light waves. 3 times 10 to the 8th is 300 million meters per second. I think this number here is a lot bigger than this number here. Now that's a rounded off number, 300 million. The actual speed of light is 299,972,456 meters per second. But we can say 300 million for simplicity's sake to make our equations a lot easier to work. And then we use the scientific version, 3 times 10 to the 8th. But we're talking meters per second. In English terms, that's 186,000 miles, not per hour, 186,000 miles per second. Remember the equation, wave speed equals wavelength times frequency. That doesn't change when we go from sound waves to light waves. So it's still V equals lambda F. However, instead of using a little v, we're now going to use a lowercase c. Remember Einstein's equation, E equals mc squared. C represents the speed of light, and that's because c is a constant. In the equations, we will always use 3 times 10 to the 8th meters per second, 300 million meters per second. Now, some people say 300,000 kilometers per second, or 3 times 10 to the 5th kilometers per second. So make sure you match the units up with the exponent correctly. Here's an example. Blue light with a wavelength of 4 times 10 to the negative 7th meters and a frequency of 7.5 times 10 to the 14th hertz. Multiply those two together, you're going to get 3 times 10 to the 8th meters per second. Now, the thing is, all light waves under the same conditions will have the same speed. And that mathematically shows us that if we increase the wavelength, make this higher, then the frequency has to go down, or the other way around. If the wavelength is smaller, the frequency is going to be higher. Now look at those numbers for light. We're talking negative 7th to 14. That's a whole lot of zeros with the negative 7 in front. That would be decimal, 6 zeros, and then the 4. And then the frequency, 7.5 times 10 to the 14th, you're looking at 7, 5, and 13 zeros afterward. So there's a very, very large range of wavelengths and frequencies for light waves. But multiply one together, one wavelength times the corresponding frequency, we will get 3 times 10 to the 8th. Ready? From the sun to the earth, here's your speed of light again, 3 times 10 to the 8th meters per second. The distance from the sun to the earth is approximately 93 million miles, and that's actually the average of the closest point and the furthest point, because remember, the earth does not go in a complete circle exactly. It's teeny tiny bit elongated. Now, in metric terms, 1.5 times 10 to the 11th meters, or 1.5 times 10 to the 8th kilometers. But we're dealing with the meters because we're using meters per second here, so that has to match. Remember, distance equals speed times time. Fill in the numbers we know. There's your equation, d equals vt. Remember, velocity, because remember, we're including the direction the light's traveling also. So here you go. With the speed of light, 3 times 10 to the 8th meters per second, and the distance from the sun to the earth, 1.5 times 10 to the 11th meters, we're going to divide to get the time that it takes for light to get from the sun to the earth. That would be 500 seconds. Divide by 60, you have approximately 8 1/3 minutes. 8.3 with a bar if you really want to get technical. 8.33 rounded to the hundredths place. Well, you have to realize, since these two numbers are actually rounded off, then that's not going to be 100% exact either, but it serves the purposes for the calculations. So it takes light approximately 8 1/3 minutes. That's 8 minutes and 20 seconds to get from the sun to the earth. Ready? Wave model of light. Light behaves like a transverse wave. You'll see pictures again. That's the wave that goes up and down, up and down. And the particle model I mentioned a few minutes ago. Light waves can emit electrons at very high frequencies. Remember, particle model also says teeniest, tiniest bits of solid material so gravity can pull on those light waves. Well, anything that has mass is made up of electrons. So light waves can emit electrons at very, very, very high frequencies. The wave particle theory of light says light comes from photons. We've talked about those before. It may be a while, but we've talked about photons before. Very small bundles of light energy, electromagnetic radiation. And, as I said a moment ago, light waves can get very slightly bent by the Earth's gravity. So the wave model of light considers waves as both energy and as mass with teeny tiny bits of particle, but just very slightly. But there's your wave model of light. Ready? Most of the light is invisible. Low to high frequency, we're going to list these in order from low to high frequency. These are categories. There are different kinds of radio waves. Okay, things used for communication use radio waves. Television, aerial, you might have to ask your parents about that because everything is more of a satellite or a cable right now. But in old days, we had to use antennas and take in radio waves to work a television set or a radio. CB, Citizens Band, this is something that truckers will use, and they have their own little lingos and codes to communicate with each other. Police and fire communications, they use specified frequencies that only they are allowed to use, and if people get caught using those without permission, they can get in trouble legally. Cell phones use radio waves. When we call each other or text each other, Wi-Fi uses radio waves. Pretty much anything that uses EM waves for communication purposes is using a radio wave. Microwaves. Okay, we've said some time back, excuse me, pause for a moment. Okay, now I'm ready. We can use microwaves to heat up our food. They can also be used in some communication devices. Mentioned the microwave ovens, the police, the speed guns that they use to see how fast we're driving, or athletes may have someone sitting in the bleachers to see how hard the pitcher is throwing or get that exit velocity off the bat. That's done by microwaves, and then the distance equals speed times time calculation. Okay. Infrared. Turn on a regular incandescent light bulb. That thing gets hot very quickly. That's infrared light coming off. Infrared light contains a lot of heat. Turn the stove burner up high. Usually you'll see a nice bright red as that stove burner gets very hot. Military uses infrared for night vision goggles and glasses so they can see the enemy or other living creatures at night when there's very little light. Okay, these are the lowest frequencies of invisible light. And so it starts with radio waves, then microwaves, then infrared waves. And then we get to the visible spectrum. You see the rainbow on there. I'm going to pause a moment. I won't pause the machine, but I'll pause my voice for a moment just to see if you can remember or identify the colors of the rainbow for just a few seconds. All right. In the middle of the electromagnetic spectrum is the visible light. So there are three categories of invisible light on the low frequency end, then the visible light, then three categories of the highest frequencies after the visible spectrum. White light is actually a combination of 7 colors of the rainbow. Okay? Gave you a moment to think about it. Now, see if you were correct. In order from low frequency through the visible spectrum to the highest frequency, these are the colors: red, orange, yellow, green, blue, indigo, and violet. And in that order, you may remember from learning this maybe in elementary school, the fake name Roy G. Biv. R-O-Y, G middle initial, and B-I-V. And that will help you remember to put those in order of low to high frequency. If you turn that around to wavelength, That's going to be backwards. And we'll come back to that in the next set of notes. After violet, then we get back to the invisible light. Okay? Ultraviolet, remember from sound, ultra means above the frequency range that we can hear, ultrasound. Ultraviolet is above the frequencies of light that we can see. The sun rays contain ultraviolet radiation. There are three categories: UVA, UVB, and UVC. UVA rays, they're the lowest frequency of those three. They give us a nice little tan. UVB, take too much of that, then you're risking sunburns. And UVC, get too much of that, you're risking skin cancer, as you see on the screen. Ultraviolet tanning lamps, be very careful using those, especially if you're not really used to those, because they can give off the higher levels that can cause sunburns and cancer if exposed too much. Dentistry may use ultraviolet radiation to kill germs inside the mouth as they're doing their cleaning and trying to prevent you from getting oral cancer. Now, you don't want too much of that, though, because too much of any kind of radiation can be bad for us. But if you get too much, especially of the higher levels of ultraviolet radiation, you're eventually risking skin cancer. So protect yourself if you're going to be outside for extended periods of time. X-rays we've talked about before. These help physicians see the bones. Calcium in the bones reflects X-rays very well. So in the image taken where there's no bone, there's no white spot because there's no calcium there to reflect those X-rays, and that's how we can tell if you have a fractured bone. Some telescopes use X-rays to zoom in on the objects in space that we're looking at. Security, we've mentioned before, to help see inside somebody's luggage to make sure somebody's not hauling anything dangerous onto the airplane or into a hotel or, where you're not supposed to have certain things. Now, these can be harmful if prolonged, so people who work with X-rays need to protect themselves. Many will wear lead vests, and others will go into a protected room and screened from where the X-rays that they have to work with are actually coming out. And gamma rays, we've mentioned before, these treat cancer cells. They sterilize medical and surgical and other hospital equipment because these things destroy cells. They kill germs, but they can also kill us. So we have to be very careful when dealing with gamma rays. Nuclear decay, we've mentioned that all the way back in chapter 8. So nuclear decay can give off deadly gamma rays. So that has to be controlled very, very carefully. But these are your higher frequencies of the invisible spectrum. Remember, visible is right in between. So before I move on, just very quickly, in low to high frequency, radio, microwave, infrared, visible, ultraviolet, X-ray, and gamma rays from low frequency to high frequency. Ready? All right, the speed of light, coming back to that, all light travels at the same speed under the same conditions. Through outer space, 3 times 10 to the 8th meters per second. Again, that's a rounded off number, 300 million, but that makes this number much easier to use in the calculations. Vacuum means where there is no air, where there is no matter. Light can travel through a vacuum, such as outer space. Now, light travels fastest through gases once you get inside the Earth's atmosphere and the phases of matter take over, where it's opposite of sound. Sound waves will travel fastest in solid materials, but that's opposite of light. Light travels fastest through outer space, and then once inside the Earth's atmosphere, light will travel fastest through gases. There's a little alliteration for you, fastest through gases. Slows down in liquids, and light will then slow down in transparent solids such as glass. Now, I'm emphasizing the word transparent for a reason. Transparent means allows light to pass through. Not all objects do, but most glass will. And objects that don't are called opaque. And objects that let some light pass through but scatter and give us a fuzzy image on the other side, those are called translucent. Those are coming up a little later on. Ready? Light wave characteristics. Just like with sound waves, there are parts of light waves. Crest is the highest point, and that contains the most energy. Trough is the lowest point and contains the lowest energy. Now, I haven't drawn on the screen, which is probably a good thing, But let's do that now. Remember that light waves are transverse. Here's your crest, and you've seen these pictures before. Here's your trough. Assume that I can draw well. All right, your amplitude is going to be, this is the medium here. Your amplitude is going to be the distance from the medium to the crest, and if I draw this correctly, that's going to be the same height also. And get a second wave started to another crest here. Wavelength, lambda, goes from one crest to the next crest, or it could be from a trough to a trough. Again, you have to assume that I can draw. You know I can't. Amplitude is the height of the wave, and the amplitude determines the intensity or the strength of the wave. With visible light, that means brightness. So a high amplitude wave would appear very bright to our eyes. But just like with sound, intensity, and loudness, brightness is a perception. What's bright to some people is not very bright to other people, but the mathematical measurement called a candela, well, that we cannot debate, just like decibel levels for sound. Wavelength is the distance from one crest to the next crest, or from a trough to a trough, but really it can be any part to the same part on the next wave. We usually measure from crest to crest, and sometimes trough to trough. So those are your wavelength, and remember lambda means wavelength, lowercase f means frequency, which is waves per second, just like we've had before. And we will measure the frequencies in hertz, Hz, just like we did before. But these frequencies and wavelengths you saw on the screen a little while ago, they can be very, very small scientific numbers to very, very large scientific numbers. But these are your characteristics and parts of a wave. Ready? The end. I hope this, brightens your day. We have 2 sets of notes left. We'll see you next time.